Assalamualaikum and hi everyone. Welcome again to Computer Science lecture. This is lecture 7. I'm going to explain to you about logic gates. So our learning outcomes today, we are going to look at all the symbols of logic gates, which involve combination logic gates also. And also you are going to look at the Boolean expressions of the logic gates, and we are going to also look at truth tables of those logic gates. And lastly, when you are given a description of something, you should be able to identify what logic gate it refers to. So what is logic gate definition? Okay, logic gate is actually a physical thing. It is an electronic circuit in which the input and output represent the statement of Boolean algebra. So I have illustrated it here. This is an example of a logic gate. Okay, this is example of a drawing of logic gate. This is not a real logic gate. Logic gate is going to be look like a chip, okay, which has many pins there. So this is example of a drawing, okay, or representation, a graphical representation of a logic gate. We draw logic gate N like this. A and B equals to Y. Okay, so this logic gate actually represents a statement of Boolean algebra, which also can be said, understood as Boolean expression. Okay, Y equals A and B. Y equals to A and B. This is Boolean expression, which is represented by logic gate like this. So this is what this definition is saying. Okay, a logic gate is an electronic circuit in which the input and output, these are the inputs A, B, output is Y. Okay, the input and output represent the statement of Boolean algebra. This is the statement of Boolean algebra. Okay, next, here we have 7 logic gates. Okay, the basic logic gates are actually AND or NOT. As we have seen earlier, we have seen 3 logical operators. AND relates to the logical operator AND, or relates to a logical operator OR, and NOT gate here relates to the logical operator NOT. Okay, and then we have combination of NOT and it becomes a NAND gate. Okay, sometimes people call it NAND gate. I call it NAND gate. And combination of NOT gate and OR gate is called NOR gate. Combination, this is not combination, this is exclusive OR gate. Okay, or XOR. Okay, XOR or XOR. And we have another one, XNOR. This is combination of XOR and NOT. Okay, so it becomes XNOR. So these are the gate names: AND or NOT, NAND, NOR, XOR, XNOR. Okay, you must remember the names, and you must remember the symbols used. Okay, this N is the name, gate N. Okay, gate N, symbol is like this. We have something drawing like a big D there. Okay, and we have 2 input. You must draw this line connects to the body. Okay, you cannot just draw it hanging there. And we must have an output line here. This is output Y. Okay, OR is drawn like this. OR gate is drawn like this. It's like what is this? So we have a curve here, and another curve here, another curve. This is called A or B. Okay, this is A, input A, B, and output Y. This is a symbol of gate OR. A symbol for gate NOT is triangle with a circle, small circle at the end. This is a symbol of gate NOT. The symbol of gate NAND is the same as N. Okay, the first part is like N, but we have a small circle here which represent NOT. Okay, so this is gate NAND. This is gate NOR. We have like something like NOR just now, like OR. And we have a small circle in the end here. So this is, it becomes NOR, because NOR is combination of OR and NOT. Right? And the expression is going to be like this. Okay, this we have seen this earlier. So for NAND, we are going to have A and B in bracket, then prime. Okay, because everything is going to be not. And A and B first, and then not. So it has to be in bracket here. So same goes for OR. We are going to plus A plus B, or A or B, bracket them, and not apply the not to it. Okay, so that's the meaning of this small circle here. It negates the output from this gate. Okay, so let's look further. We have two more. Okay, we have XOR and XNOR. XOR is drawn like this. It's like OR, but we have another curve in front here. Okay, so it's just the same as OR, but we have another curve here, and the expression is written like this. Okay, we have a circle with a cross, a plus inside there. Okay, so this is called XOR. This is the gate name XOR. Gate symbol is like this. This is the Boolean expression for XOR. XNOR, we draw like XOR, but we have a small circle to indicate not, because XNOR is a combination of not XOR, and the expression is written as like XOR, but we bracket them, bracket it, and we put prime there to indicate that not XOR. Okay, logic gates, input and output. Okay, a gate will have one or more binary input. Binary means 1 or 0. A gate will have one or more binary input of 1 or 0, but just one binary output. Output cannot be more than 1. Input can be more than 1. Okay, input can be 2 or more. Or input can also be 1 for a certain gate. Okay, for what gate? Okay. For NOT gate, we have only one input. All gates, okay, the second one, all gates except NOT gate commonly has 2 input and 1 output. Right. Input and output are labeled as a single uppercase alphabet, such as A or B or C. So we cannot use a name like AB for an input. Okay, because it will be confused. Okay, it will lead to confuse. So we use only single uppercase alphabet, uppercase letter. Truth table. Okay, let's look at the definition first. Truth table is used to show the function of a logic circuit or logic gate. Okay, to show the function, it means to show the output for all possible combinations of input. Okay, like we have seen in the previous lecture, it shows the possible output for all the possible input. Okay, if we have 4 possible input, what are the output for those? It's going to be summarized in truth table. For a logic gate or circuit with n input, there will be 2 to the power of n rows in truth table. So let's look at this further later. Each row will represent a different combination of input state, and the output must be evaluated according to the precedence of the operators. Okay, because the circuit may involve many logical operators. So let's look here to understand more. What it means by that is, here we have 2 variables only, which means we have 2 input. Okay, so the truth table is going to have 4 rows, because 2 to the power of 2 is equals to 4. 2 to the power of 2. Why 2 to the power of 2? Because 2 input, A and B. Okay, so we have 4 rows, and in this truth table, we summarize all the possible combinations of input. We may have 0, 0, 0, 1, 1, 0, 1, 1, and no more than that. Okay, and for those possible inputs, we are going to write what are the output. Okay, for 0, 0, because this is n, 0, 0 will produce n, 0, 1, 0, 0 will produce 0, false. 0, 1, 0, 1, 0 is 0, 1, 1 is 1, because this is n. N will become true only when all the inputs are true. Okay, this is what you have to understand. Okay, now for the second one, or, okay, or must have at least 2 input, at least 2. Okay, it can be more, but at least 2. So here in this example, we have in this gate, okay, the basic gate of OR, we have 2 only. So we will have 4 rows, because 2 to the power of 2 is 4, and the possible inputs are the same as in n truth table, 0, 0, 0, 1, 1, 0, 1, 1. And here, for 0, 0, we have 0. For other combinations, we will have 1s, because for OR gate, okay, or OR operation, if any one of the input is true, then the output will become true. Okay, next is for NOT. For NOT, we have only one input for NOT, to apply NOT. Okay, so when the input is A, because it's only 1, we will have 2 to the power of 1 rows, which is 2. 2 to the power of 1 is 2. So we have only 2 rows here. One possible input is 0, another possible input is 1. And the output for 0 is 1, the output for 1 is 0. Okay, so these are the truth table. Let's look further for other gates. For NAND gates, okay, still we have 2 possible input, 2 input. We have 4 rows, 2 to the power of 2, and the output now will reverse the n, okay, the n output, because none is not n. So 0, 0, 0 and 0 will produce 0, but now is not n. Not 0 is 1. Okay, 0, 0 should produce 0 and 0 should produce 0, but none applies not to that output. Not 0 is 1. 0 and 1, we should get 0, right? But not 0 is 1. 1 and 0, we should get 0, but now we apply not to it. Not 0 is 1 also. And the last one here, 1 and 1, true and true. Now we should get true. True and true is true, but we apply not to that. Not true is false. Alright, so we have 1, 0 here. This is just the reverse of the previous one. If you look at n is 0, 0, 0, 1, but none is 1, 1, 1, 0, because none is the reverse of n. For no, it's the same as none just now. It reverses the output of all. Okay, 0 and 0, we should get 0, but reverse that 1. 0, 1 is 1, but it becomes 0. 1, 0 is 1, but it becomes 0, because not it. And 1 in 1, true, true, we should get true, but now it becomes false, because not true is false. Okay, I hope you understand this. I'm going a little bit quickly. Now the last one, the last two is XOR. For XOR, I have to explain a little bit. XOR means it's going to become true only when either one is true. Okay, when A is true, B false, it will become true. When B true, A false, it will become true. But it will not become true if both are true. So 0, 0 will become 0, 0, 1 will become 1, 1, 0 will become 1, 1, 1 becomes 0. XOR needs 1 only to become, one input true will become true. Okay, and XNOR will reverse that. XNOR will reverse the XOR. Okay, you just evaluate like XOR and then you reverse it. So we will have something like this.